In this video, I'll walk through an example of decision tree learning and just look at one node and specifically compare two different splits we can do on this node, two different parameters that we can put in this node, and how the relative entropy plays into choosing which one would give us more information at any particular point. So this idea is related to the idea of entropy. And again, the definition of entropy is that if we have a variable v with values vk and probability distribution p of vk, and the entropy was defined as the sum of p of vk, it's the sum overall k, times log of 1 over p of vk. We said that this is a value that correlates, or that sort of relates to how non-uniform the distribution is and how much information is in this distribution, and also if we take the log of 2, how many bits we need to transmit one variable of the distribution on average if we use the most efficient encoding for this distribution, for this variable. So let's kind of just see what this looks like for a binary variable. We put this sort of general definition to the side here. And for a binary variable, we have a variable that has a probability of p to be true. So probability of true equals p, and probability of being false equals 1 minus p. So if we take this same function, so the entropy for this probability would be p times log 2 of 1 over p plus 1 minus p times log 2 of 1 over 1 minus p. We can easily see that if the distribution is half and half, sort of like an even distribution, then the outcome of this this formula, which we will call b of p, so the outcome of this formula would be half times log 2 of 2, which is 1, plus half, which is also half, times log 2 of 2, which is 1, and overall it's 1. So generally speaking, even distribution has an entropy of 1, meaning that it's uniformly distributed. And the more unevenly distributed it is, if this is really small, let's say 0.01, this is really big, the more unevenly this is, the more this value b of p goes towards 0. So at the extreme limit of having a distribution of 0 and 1, we can say that this kind of goes towards b of p being 0. And this is obviously symmetric, so even if it was 1 and 0, so this is a symmetric relationship. So let's just retain this kind of formula which we want to use in our example. Let's move it off to the side. In this way we can look at the example of the restaurant waiting. Here we have our example, and since we see that the distribution of the whole population is kind of half of our examples have waited for a table, half haven't waited, so this is kind of our before situation. As we said before, the entropy we have, or the information that we have before we decide to split on one of the variables is going to be 1. So let's write this in here. So b up here equals 1, and the same for here, b equals 1. So let's say we decide to split on patrons, which we already know intuitively is the right split. And we'll calculate the average b value after the split. So the average p-value after the split And let's do this calculation in full. So the b value for none is going to be as follows. Since this is a completely biased distribution, so it's a distribution of where p is either 0 or 1, depending how you count it. We already said that b here equals 0, and the same for sum, b equals 0. So what is b for the full situation of patrons? It would be 1/3 times log 2 of 3 plus 2/3 times log 2 of 3 over 2. And that comes out to 0.92 approximately. So b here is 0.92. Let's just draw this in here. And what is the average information after this? So we're going to weigh this by the size of this distribution. So it's going to be 1/6 times 0 plus 1/3 times 0 plus 1/2 times 0.92, and that comes out to approximately 0.46. So 0.46 is the information that we have after you split on this variable. The other one is going to be much faster. We know that for each of these distributions, for each of the values, the outcome is going to be 1 because they're all evenly distributed. So really what we have here is b equals the average b equals 1, whereas the average b here equals 0.46. And this is what we call the information gain. So this moving from this 1 here to this 1 obviously says that we didn't gain any information, which is true because we're still split 50-50 on whether the person is going to stay after we chose this variable. Whereas here we have an information gain of 0.64. Sorry, 0.54. Which is the information gain that we have moving from this 1 to this 0.46. And this means that between these two variables, patrons is a better variable to split on at this stage than type because we have a bigger information gain. And in fact, in the example that we have in the book, this is the best thing we can split on. This is the highest information gain we're getting of all the variables that we had. So hopefully this walkthrough kind of explains how we, in fact, decide which variable to split on at every point. And once we split on this, we can prune the tree here and here. And we do the same process again with this part of the tree and looking at other kinds of variables that might help us decide, and based on which gives us the biggest information gain as calculated in this example.